Hi everyone, thanks for coming to my talk. Today I'm very excited to share with you some of our latest progress in scaling up distributed deep learning systems. I think everyone here have just witnessed in the last decade the fascinating progress that we are making in deep learning systems. And part of that is enabled by increasingly large dataset and increasingly available computation powers. And our computation capacity has also been increasing in very rapid speed. Just 6 years ago, all you can get on Amazon Cloud is a single machine with 5 teraflops on it. And today, if you go to the same cloud, you can get a machine that's way more beefier than that. Because of that, what used to take weeks for a user to train now only take hours. However, since we have more and more computation available to our user, they are also start to train larger and larger models over larger and larger datasets. I think for everyone who's here today, one question that we all think about is actually how can we build a machine learning system to accommodate this ever-growing demand of machine learning training over ever-growing scale of data. If you look back in the last decade, we can see two lines of effort. On one hand, there is a lot of researchers try to do amazing work to try to propose new algorithms for distributed training. How can we design a better model? How can we design a better training algorithm? How can we design a better training optimizer? On the other hand, there is the system line of research that take as input an existing algorithm and try to scale it up. In this talk, we are going to scope ourselves to distributed learning with data parallelism. Essentially, I have a whole bunch of workers. Every single worker holds a partition of the data, and jointly they train a single machine learning model. If we take this scope, we can see on one hand, there's an amazing collection of systems that is available today to help users with this type of training. For example, Uber's Hello World, BytePS from ByteDance, so on and so forth. On the other hand, researchers in the machine learning community have also been working on new algorithms to decrease the communication overhead for distributed learning. Today, we can train an algorithm in a decentralized way, in an asynchronous way, or in a communication efficient way. However, if you look at these two different lines of work, we realize there exists a gap a couple years ago. That is, if you look at all those amazing systems, many of them do not give you a systematic support of these amazing latest technologies. This inspired our effort, which really try to understand, can we build a single machine learning systems that is flexible and generic enough that we can support all of these state-of-the-art communication optimization technologies. So this is what we built. We built a system called Bagua that support the following functionalities. On one hand, we have different communication patterns that you can use. We have the standard centralized communication patterns where all the machines talk to a central server and communicate at the same time. We also support asynchronous communication patterns where all the machines do not need to wait for each other, and we also support decentralized communication patterns where all the machines only talk to its neighbor. On the other hand, we also support a whole bunch of communication channels. For example, you can communicate between two different machines in a lossless way. However, you can also do specification and also quantization. The goal of the Bagua system is to make sure whenever the user gives me a subset of these communication patterns and a subset of those logical communication channels, we can put them together to form a new communication pattern, for example, decentralized, asynchronous, and lossless communication, and we can plug it into your existing deep learning training stack such that you can train your machine learning model using this communication pattern. So this is what we have been doing over the last couple years. We have been doing this for a couple years, and we realized there are actually 3 different challenges, and in this talk, I'm going to talk about them one by one. First is the theory and algorithm, because if you want to support different communication patterns, you need to have different algorithms to support each one of them. And in this talk, I'm going to show that it is actually possible for you to design algorithms to accommodate different communication patterns. And today, if you give me one communication pattern in the previous slides, I kind of know there exists some algorithms, either developed by us or by other researchers, that can get it done. Once we have the flexibility of communication, we can try to understand how can we cache in to really bring performance benefit. So on this part, I'm going to try to convince you that it is possible to automatically optimize for the performance of this diverse set of algorithms in a single framework. And then I will present some empirical evaluation results to try to convey two messages. First, once you support this diverse collection of algorithms, it is possible to outperform existing systems. And second, once you support this diverse set of algorithms, you can also accommodate different diverse network conditions, such as network with high latency, with low bandwidth, with existence of straggler, so on and so forth. Okay, so let's talk about theory first. Here, the thing that we are curious about is for different communication pattern, what algorithm should we use to train a deep neural network? And we have been doing this for a couple of years based on many fascinating results by different researchers, and they are summarized in this very small monograph. Essentially, this is how we think about this. Different algorithms have different convergence and system profile, so let's walk through some of them. If you think about the standard data parallel SGD, it is actually not that hard to write it down. On every single worker, it actually only do 4 steps. First is try to synchronize the model with all other workers, and then it get a local copy of the data, either a batch or single data example, and then calculate the stochastic gradient, and then update the model. Each worker doing these 4 steps again and again, and you get your machine learning model at the end. So when you try to design the algorithm for this process, there are actually 2 fundamental questions that we are curious about. First one is whenever you are moving data around between different machines, what is the precision of data movement that I can tolerate? And the second question is whenever you are synchronizing your model, what is the property of this synchronization primitive that I can tolerate such that I can still converge to a very similar result? So this is the basis of our exploration. You can always have the standard centralized synchronous lossless stochastic gradient descent pattern. Here, whenever you are trying to synchronize your model, you are actually doing a synchronous average among all the workers. And whenever you are sending information between one machine to another machine, you are doing lossless data movement. You do not quantize, you do not specify it. The high-level idea is distributed batch gradient calculation can be distributed to multiple machines, and also all the workers try to synchronize with either a central server as parameter server, or they are going to use the MPI primitive that is all reduced. And this is a mathematical formulation, right? It looks very simple, right? xt plus 1 is a model at the time t plus 1. It takes a previous model and update it using the sum of all the gradient it collected from all the machines. If you think about the convergence behavior of this, it actually have this convergence rate, where n is the number of machines and t is the number of iterations. If you think about the system profile, it usually starts with one chunk of computation for the forward and backward path, followed by communication and also by computation of the next iteration. Whenever we are trying to understand alternative design for these 2 questions, one, the synchronization primitive, and second, the data movement procedure, our goal is try to maintain similar convergence rate. However, try to make the system run much faster. This is a game that we are trying to play. Once we decide on this goal, there are a lot of things that you can relax during communication. For example, you can quantize all of your communication payload, and then you hopefully can accommodate a network with less bandwidth. In this case, your communication primitive is still a synchronous average. However, whenever you are moving data, you do a lossy compression. So this is a mathematical formulation, and you can see it's very similar to the textbook stochastic gradient descent, and the Q is the quantization function. And if you look at the convergence behavior, right, we introduce this additional term, right? Hopefully it is smaller than the first term, so empirically, hopefully it won't hurt you too much. And you can remove the synchronization barrier to have something asynchronous. In this case, your communication primitive becomes an asynchronous average, and whenever you are moving data around, you do not have to quantize it. Mathematically, it is equivalent that every single worker have access to a styled model, and in the convergence, we actually introduce a higher order term that hopefully empirically won't hurt you too much. You can even remove the centralized barrier and have a decentralized communication pattern. In this case, each machine only talks to its neighbors. And of course, whenever you are moving data around, you do not have to quantize it. If you do this type of decentralized communication, you can also have some algorithm to give you the convergence guarantee that look like this. Introduce another higher order term in the convergence rate. What's interesting is if you start to put them together, it's actually not that trivial to combine them. So let me show you a very simple example. Assuming I want to do the following pattern. I want to do decentralized communication, but I also want to do quantization during communication. If you simply conduct quantization to the decentralization algorithm that we showed in the previous slides, it actually doesn't work too well. In this case, you kind of need to twist the algorithm to make sure you are quantizing the update of a model instead of the model itself. Nevertheless, it is possible to come up with some algorithms with this convergence guarantee. It introduce another term in the convergence rate, but hopefully, empirically, that won't hurt you too much. After a whole bunch of explorations over the last couple of years, and also after study from different researchers, at the end of the day, we have a family of algorithms with the following property. They all have comparable theoretical guarantees, and many of them have comparable empirical guarantees when you run them on real-world applications. However, they rely on different communication patterns, and they have very different system profile, which is how long does it take to run each of those iterations. And if you think about communication as a process governed by three different factors, the latency, the bandwidth, the synchronization barrier or existence of straggler, you can see which communication pattern benefit which different scenarios. Assuming you have heterogeneity, right, asynchronous communication pattern often works better. When you have a high latency network, maybe you should try the decentralized pattern. When you have a smaller bandwidth in your network, maybe you should try the quantization pattern. And then if you have network with multiple of those properties, you can also combine these different communication patterns to train your machine learning algorithms. But whatever communication pattern you decide to use, after years of exploration, we believe there exists some algorithms can accommodate that. So once we get the flexibility from the theory side, let's talk about the systems. How to build a single system to support all of those communication patterns. Here, what is the challenge? The challenge is that if you just give me a naive implementation of all those algorithms, often the time you cannot observe any speed up over state-of-the-art systems. So essentially, to take advantage of the flexibility provided by the system relaxation, we need to carefully optimize the system implementations. If you look at what existing system is trying to do, they often take one specific communication pattern, that is the standard data parallel SGD, and optimize the communication and commutation. And there are a lot of smart tricks that they can do. For example, if you think about a vanilla implementation of distributed SGD, it kind of looks like the following. You do the backward pass of the last layer, and then you communicate its gradient, then you do the second last layer, communicate the gradient, so on and so forth. Once you communicate all the gradient, you update your model, and you start the forward pass of the next iteration. If you look at Hortonworld or TorchDDP, what they are trying to do, they have a very smart technology to batch all of those communication together to form a larger tensor to communicate, and also try to hide the communication behind computation to do this concurrently. And then after they finish all the communication, they update the model and move on to the next batch. If you think about batch PS, they actually have also very smart technology. Essentially, they break down the communication into different small chunks and try to understand from the data dependency graph how to best schedule these communications together with computation. If you think about this, what is the challenge of applying all those technologies to our scenario? The challenge is that since we want to support different algorithms, they all have different communication and computation patterns. I cannot optimize our system for each specific algorithm. Instead, we need to try to understand how can we have a single optimization framework that can be automatically deployed and applied to all this diverse set of algorithms. So that is what we have done when we try to design Bagua. We have two design principles. First one, we want to have a modular design to accommodate the diversity of different algorithms and communication patterns. And second, we want to have a single optimization framework that can be applied automatically to an algorithm implemented within the Bagua framework. From the user perspective, Bagua looks very familiar. The user gave us a dataset and also gave us a neural network architecture, for example, a PyTorch program. And then if you have one algorithm in Bagua, it looks like the following. It contains a whole bunch of hooks at the forward and backward paths of each layer. And when you implement each of those hooks, you can actually use a whole bunch of communication primitives that we provide inside the Bagua system. All those communication primitives have a style very similar to MPI, but we extend the standard all reduced semantic to support different communication patterns. For example, we have one operator deal with low precision, centralized synchronous communication with error compensation, so on and so forth. Once you have that, Bagua has the memory manager and execution manager to try to automatically optimize the execution. I will not go into the detail, but at a high level, this is what this optimizer tries to do. It's going to take as input some communication and computation pattern of some algorithm implemented inside Bagua and try to automatically batch all the communication that it can batch together, and also try to schedule this communication with computation to make sure we can have as much communication as possible. All of this process is done automatically without any intervention from the developer. During the process of building Bagua, we actually learned a whole bunch of lessons about how to construct such a system. And by just applying this high-level principle of automated optimizer to Bagua is not really enough, and there are actually a lot of engineering work that we need to do. So in this talk, I'm not going to go to detail here. We have one paper on archive, and you can just look at it about all the tricks that we play when building Bagua. As the last part of this talk, let me give you some empirical result. So we tried this on 16 machines. Each one of them have 8 V100 GPUs, and we try to connect them with different type of networks, 10 gigabits, 25 gigabits, and 100 gigabits. As you can see, over this diverse range of applications, even if you relax the communication pattern from Bagua, we essentially get the same convergence behavior compared with other systems. Essentially, we need the same number of iterations to reach the same accuracy. However, because we do relax the communication patterns, you get a speed up. Under different network conditions, you can actually get up to 2 times speed up over state-of-the-art deep learning systems. So essentially, by supporting this diverse set of algorithms, we can provide significant improvement over existing systems. So supporting this type of systems really pays off. But what's more interesting is because now we have a diverse collection of algorithms, we can actually accommodate different network conditions. For example, if you have a network with kind of higher latency, for example 5 millisecond latency, you can see we have decentralized algorithm to really work reasonably well under this scenario compared with all other systems. If you have a network with lower bandwidth, for example only 5 gigabits, you can see those quantization-based method can also work well. When you have a network with both high latency and low bandwidth, you can have the decentralized quantized pattern for that purpose. And when you have straggler inside your system, you have heterogeneity both in computation and communication. The asynchronous communication pattern also works well. So this is what inspired us to design Bagua to support a diverse range of algorithms to accommodate different network conditions. So this is what we have. Essentially, I present the Bagua system, which try to support what machine learning community has been working on over the last decades, try to provide systematic optimization and support for state-of-the-art training algorithms. So Bagua is currently open source here, and it would be great if you can play with it. We are looking forward to hear your feedback and criticism, and I'm happy to answer whatever questions that you may have today. Thank you.